Hello friends, welcome at my channel. Today I would like to explain to you the basic idea of derivative. So let's pretend we are riding a bicycle, and since I'm right now in Turkey but normally living in Düsseldorf, let's pretend we're riding a bicycle from Düsseldorf to Amsterdam, which I've done many times already. And let's say we start just at, I don't know, at noon, and there are approximately 240 kilometers to Amsterdam. And so at the beginning, we're kind of very ambitious and have a lot of energy, and we're pretty fast. So we are riding quickly, and then we're getting a bit of gas and getting slower. And so the curve of our travel looks like this. All right. So let's pretend this is the case. So we start at noon. Let's say it's 0, and 24 hours later, we are arriving in Netherlands, in the capital of Netherlands, in the beautiful city of Amsterdam. And so, if we only know that we travel for 24 hours and the distance between those two cities is 240 kilometers, then we can only figure out the average speed, which is, let's say, we had like 100 kilometers on our computer and now we have 340 kilometers. So it's 240 in between, and there is a slope looking like this, which connects those two dots. So the thing is, the average speed so far would be 10 kilometers per hour. We would divide 240 kilometers by 24 hours, and the average speed would be 10 kilometers per hour. As you can see on the picture, the approximation is pretty bad. There is a huge discrepancy between the curve and the slope, so the line. Maybe we should just somehow improve it. And the answer is yes, we could. Imagine we would exactly know where we are 12 hours after the start. So we are somewhere here. Normally, if you're familiar a little bit with the geography of Germany and Netherlands, you know that like there is a beautiful city as well, exactly on the border to Germany, which is, I hope I pronounce this correctly, Nijmegen, with the best astronomy faculty in Netherlands, which I do know because I visited this university a few times. It's wonderful as well. So this is the city of Nijmegen, and let's pretend I've been there. Uh, I was here just exactly 12 hours after I started, and so now, since we have 2 points already on our curve, we can produce two lines. That would be the first one, and that would be the second one. So that's the story, all right? And so we have now a way better approximation of the curve because we have just a point in between, which allows us to produce, well, way more closed approximation of the curve. Now the game is clear. If the interval is getting smaller, like 6 and 18, the improvement is getting better. So we're getting here a point somewhere, and we're getting also here a point somewhere. So that would be looking like this. And as you can see, at some point, maybe we would see no big difference between the curve and our lines. And this is exactly the point where we want to get. So what we have are the seconds, and those seconds are getting closer and closer to the curve. And the thing is, we are willing to decrease the length of the interval, and doing so, we are increasing the number of intervals, and the approximation is getting better. Now, considering our example with the bicycle, what does it mean? Well, that means that the interval is getting smaller. 24 hours at the beginning, 12 later on, then 6, maybe 3, then 1 hour, then maybe 10 minutes, then maybe 1 minute. But at some point, the interval is so small we cannot measure those 2 points anymore. We cannot distinguish them from each other anymore. And at this point, the speed is getting perfect. The measurement is getting perfect. Why? Well, imagine somebody is calling you on the phone and you are not like producing the average speed, which is 10 minutes maybe. So you are starting right now, and 10 minutes later, you are telling me the distance that you traveled. But rather, you are telling exactly at the moment you can measure it on your computer on your bicycle how fast you are. So that would be not the average rate of change for the 10 minutes, but that would be the momentarily rate of change, which is exactly the idea of the derivative. Let me write it down mathematically. So the idea is, if you have a curve which looks like this, you have one point xo. So this is the corresponding value of the function f of xo, and the interval has length of h. That would be xo plus h, and that would be f of xo plus h. So what would be the slope in this situation? That would be f of xo plus h minus f of xo divided over the length of the interval, which is h. So in this case, that would be this slope, as you can see. And if we put the limit in front, we are just kind of asking for the h to be as small as possible. So what is happening is actually the second point is now wandering towards the first one. We're somewhere here. In this situation, the second is getting better, but it's still not perfect. It's getting closer, it's getting better, but it's still not perfect. And then at some point, there is no possibility anymore to distinguish between the 2 points. Once we get there, the second is becoming to a tangent. And we are looking for the tangent line, because once we have a tangent line, this is perfect. That would be a perfect approximation. So this is exactly the idea. We call it the first principle in mathematics of the derivative. So the idea of switching from the second to the tangent is very important. Otherwise, there would be no computers, no electricity, whatever. So everything is depending on this idea. And as you can see, if we have a very tiny small interval, then the approximation is getting perfectly, but only at this point. So this is the first idea. There are 3 more important ideas, at least for the purposes of the school mathematics. If we're getting higher than high school mathematics, then there are many more, at least 20 more ways to write the derivative, especially in the multivariable case. We'll talk about it as well, but let's stick to the first 4. So the first one I already explained. Let's consider the second one. The second one is the so-called h-Methode. That means actually the same. So you have a curve. Let's take another one. This is xo, and that would be f of xo, and that would be x, and that one would be f of x. So what will happen here is actually we're producing the slope as well. In this case, we're having f of x minus f of xo, and we are dividing it by x minus xo. And once again, we wanted this interval to get as small as possible, which means we're asking for the distance between x and xo to decrease. We are asking x to become as close as possible, to get as close as possible to xo. This is exactly the idea of the derivative once again, but now this is the h-Methode. So you see exactly the same picture, exactly the same approach, just differently written. Why it is important, we will see. So there are some cases where the h-Methode is rather easier to handle than the h-Methode, and vice versa. But we are going to do integration as well, and for these purposes, the third method, the delta method, is important also. Let's see. So this is the curve. We start at xo right here. That one would be the unknown value. We don't even have to know the name of this point. We just only know that this interval is delta x and the height is delta f. All right? And we are producing such a slope. And so the derivative is delta f divided over delta x. We're having a limit, and we're asking delta x to become as small as possible. This is, once again, the idea of the derivative, which we're going to use for the purposes of the integration. And the last one is also important for the integration. If we have the same picture, but like this, we have xo here, and we have f of xo there. And, we're just moving by the very tiny small step to the right, which we call dx. And we are moving by the very tiny small step upwards, which we call df. So df divided by dx is actually the idea of the infinitely small rate of change on the very small interval. This is exactly the um, derivative of f at xo. And for these purposes, you see I was trying to write limit, but it's not correct here. We don't have to write limit. df divided by dx is already meaning that the intervals are very small. So these are four basic ideas of the differentiation. As you can see, they're actually all similar. There is just a different way of notation, but they're going to be pretty useful for us in the future. So I start a new series now about the derivatives, and I'm going to tell or maybe prove all the rules from the scratch, like from the very beginning, and we're going to be talking a lot about the limits in the future. So stay tuned. I hope you learned something, and greetings from the sunny Turkey. See you guys.